Welcome to this special edition of C++ Weekly. I do not plan to make interviews a regular part of this channel, but if you are interested in being interviewed, feel free to contact me. Today, I will be interviewing Stephen Barry about his project, Glaze. Stephen enjoys writing high-performance modern C++ libraries. His areas of expertise are signal processing, aerospace simulation, software architecture design, algorithm R&D, and machine optimization. He is the author of the open-source Ascent differential equation library and the Glaze JSON library. He is passionate about C++ and writing the most efficient code possible. So welcome to the channel, Stephen, and welcome to experimenting with me with this first ever interview on C++ Weekly.
Yeah, thank you, Jason.
You say in your bio that you're passionate about writing the most efficient code possible. And I was wondering how you balance the most efficient code possible with undefined behavior and other concerns in your code.
I think I'll just first mention that often having a goal of efficiency ends up driving towards good solutions in coding.
Okay.
But I do tend to put boundaries on trying to make things cross-platform and using the language and as cross-platform way as possible. So that typically means even in Glaze, we don't use SSE intrinsics.
Okay.
Instead, we do tricks like work on just convert our character buffers into UN64s and then work on those. So we're working on 8 bytes at a time. And then using automatic vectorization as well.
Wait. Sorry. Can you repeat that for how you? So you're tricking the compiler into vectorizing your code. Did I understand that correctly?
Right.
Okay. So could you repeat that again? How you do that?
So for example, you might want to find where a quote is inside of a chunk of characters.
Right.
So you can actually you can just mem copy a chunk of characters into a UN64, and then do a binary cast on that thing, you can do doing kinds of bit shifting. So you can shift and do XORs and figure out where that quote exists. And so you can do that on 8 characters at a time instead of just 1 character at a time.
Interesting. And that actually is better performance than doing just the nested loop and letting the optimizer try to sort it out?
It's significantly faster, yeah.
Okay. And you're doing a copy from one to the other. So we're not talking about a Reinterpret Cast or something else that's going to make me raise my eyebrows.
Right. So try to avoid all undefined behavior by doing mem copies. There is one case in Glaze where we do undefined behavior.
Okay.
And that is, everything's null terminated, and we know OSs have page boundaries.
Okay.
You have to pad your string if you're going to read these chunks, if you're going to read 8 characters at a time. We know we're already going to be padded, the page boundary is going to be valid. But we'll actually read beyond that null character into memory. We never actually use that memory. We just read that memory because we'll figure out where the quote is inside the valid distance, and we know our distances. But we'll actually read beyond the, if you have a string or a C-style string, we'll read beyond it as long as it's within the page boundaries.
So from a C++ perspective, you're in undefined behavior because you're reading past but you are saying, I know enough about the operating system that it'll probably be okay.
Right.
Okay.
And we never actually use that data anyway. It just allows us to align our things 64.
Right. Okay. Interesting. Well, since you've gone ahead and mentioned already Glaze, I wanted to start with Ascent because that's one of the project you've had around for a while, right?
Mm-hmm.
So would you like to tell us a little bit about it?
Yeah, so that's written really for low-level ordinary differential equation solving.
Okay.
So this is particularly for the physics, aerospace, chemistry kind of world where you're trying to get an exact solution. Also satellites, that kind of thing. Often you have in games, people understand you have a position and a velocity, right? And typically what will happen is you'll just say, okay, this is much time passed. I'll just do my position plus my velocity times how much time elapsed. Right? And that's my new position. Well, like in real physics, in the real world, we also have acceleration we have to care about, right? Because velocity is changing. And then the way these things change they're actually polynomial in behavior. So you can't just linearly interpolate or extrapolate, essentially, is what you're doing with Euler integration. And that's what a game typically does. It's just going to linearly extrapolate and say, this is my next position based on if I just propagate linearly.
Right.
That's incorrect in the real world because everything's continuous systems in the real world. So you have to use higher order integrators, which make your computations more expensive because you have to reevaluate the state more often. But then you can start projecting out more accurately as if you had a polynomial of like that velocity acceleration profile. So that's what it's for, solving those kinds of differential equations, getting an accurate physics simulation.
Okay. So it sounds like this is not intended for real-time use.
You can totally use this real-time.
Okay.
So there are different, so you might have heard, I don't know how much you know about differential equations or.
Well, I know however much I remember from when I took differential equations in college back in the late 90s.
Right. So there are certain methods for the most commonly used integration algorithm is probably Runge-Kutta or fourth order.
Okay.
That one, what it will do is it'll sample the current time. It'll then sample a half step in the future twice, and then it'll sample at the full step.
Okay.
You can't use that real time because you're having to sample in the center 2 times, and time is moving forward in the real world. But there are integration algorithms, which are part of the library as well, which don't have multiple samples at the same time. So as long as you can do your calculations and then sample again inside the time difference that you're doing your integration at, then you can run real time, no problem.
Okay. Wow. So is it currently used by any real world projects?
Yeah. So I recently changed jobs. My previous job, I was building simulation architectures for aerospace.
Okay.
And so there's actually 2 different aerospace engines that use the same library underneath as the core.
Okay. So they're both using Ascent, you're saying?
Right.
Okay. So I've heard some variation of game programming as a really fast physics simulation, or physicists make really slow games or something along those lines. And I don't know, it just seemed to
games are typically designed just to look okay and run really fast.
Right.
But then when you have to solve it really numerically correctly so that you're accurate to the millimeter, then you have to use these more advanced algorithms. But they also, I was going to show an example, but.
Yeah, we should, for the sake of the people watching this later, we should point out that we were going to attempt to do some screen sharing, but that failed.
But sometimes even in the game world, you have to solve things correctly.
Right.
Because what ends up happening is if you have something like, if time is a factor in your derivatives, and you have a feedback system, or in control systems, where if you're doing a controller, then if you do proper numerical integration, then your system will go unstable. And so your solution will, in a very short period of time, just explode. And you'll actually you just go completely unstable. And so in order to actually get a real simulation that works, say you go in your game, you wanted springs and dampers. In order to get that to work, you might actually need to solve the differential equation.
Okay.
Or your game will just explode every time you try to run it.
Okay, that makes some sense. Yeah.
Normally, there's additionally ways they cheat and break physics in order to get those things to work faster. But
cheat and break physics.
Yeah.
Which is not something that your software can afford to do.
Right.
And I have a question. It might be, I don't know, somewhat silly. I'm not sure. But do you do any symbolic solving of the differential equations before the numerical, or is it just all a numerical solver kind of thing?
This is all just a numerical solver. Doesn't do the symbolic side. So I would use symbolic calculators often and then plug those solutions in.
I see. Now, from the perspective of actually using this solution solver from a C++ perspective? Like, what does the interface look like? Can you just give us a high level?
Yeah, so there's actually, Ascent has 3 different ways, because again, it's super low level of solving differential equations. And so people who understand this kind of world in math understand there's a state space representation that you can have for a system. And that's where you can basically build matrix representations of how your differential equation looks like.
Okay.
That's what the library ODE int, the part of Boost,
Okay,
is built to solve it in state space format. And so Ascent also actually uses just the exact same API as ODE int for that. So you can just swap them out. However, it has 2 other ways of solving. The 2 other ways are so that you can make modular simulations, which means I don't want it state space. I want to be able to say, over here I have maybe some aircraft that has position, velocity, acceleration, and then I have another one, and I want to create and destroy these things on the fly.
Okay.
With like ODE, it expects the entire state to be in a single vector.
Okay.
With the modular approach, you can have these differential equations all be a part of the same system, but the memory is all fragmented.
Okay.
And so there's one way that Ascent gives you, and that's you can wrap a vector around these parameters, which basically act like doubles, but are registered into a single vector. So it keeps vectorization alive. Another approach is to totally fragment memory and actually have inheritance. You inherit from this module class, and it allows you to just have your memory live wherever you want for all these different entities that need to be integrated. Okay.
Yeah, that's, had a conversation recently where this topic came up, basically about, inheritance and what are the performance costs there. So just out of curiosity, have you done any direct apples to apples comparisons of, someone using like the inheritance model versus someone using the like everything is all in one giant vector model, and how does the performance compare?
Yeah, with the differential equations, and particularly if that's your expensive part of your simulation, it's actually solving the ODE.
Right.
Then vectorization is extremely helpful, because you'll basically, for doubles, you get 2x performance boost on
Okay.
most any laptop now. Same thing if you can do floats, then you have a 4x performance boost, and it pretty much is exactly like that. And so it's not so much going to inheritance; it's more just, are you allowing vectorization because you're storing all the memory in one space, or are you fragmenting that and not allowing it to vectorize? That's where the biggest performance difference for the numerical integration side is.
Okay.
But the more I do development in C++, the more I avoid inheritance.
Right. Yeah, that's a topic I hear people repeat fairly often. Yeah.
And so that's actually one direction, like future version of Ascent. A goal of that is actually to remove the inheritance and to use some things we learned even from writing Glaze and using more variants.
Okay.
To replace the inherited structure.
All right. We've got a couple questions now. I couldn't remember what my last question was a moment ago, but you just mentioned float will give you 2 times performance improvement over double. And that's because the FPU can literally operate on 2 times as many things at once, right?
Right.
Float tends to be 32-bit on every platform right now, and a double is 64-bit, right?
Yeah.
Okay. So I have so many questions. In your experience as an actual, doing physics simulations, is float good enough?
Not generally. So pretty much we use double everywhere. And then only in very specific cases, if we know float is sufficient, then that algorithm might be switched to float.
Interesting.
But pretty much we use double everywhere.
Have you looked at all? Now, see, I'm assuming this is now going to be meaningless to you, but I was just made aware of the fact that C++ 23 added 2 new float types. So we've got float 16, B float 16, and float 16.
Mm-hmm.
Yes. Have you tried using those new float types with your library? And I'm just kind of curious, what does it do there? Like, does the compiler still know how to vectorize those 16-bit floats?
I have not tried using those new float types, particularly because for physics simulation world, there's just not enough information there.
Right, right.
But I could see it being really helpful for the graphics and audio world.
Right. Yeah, I think it was mostly added to support like offloading
Machine
AI to
learning too, yeah.
GPUs. Yeah.
Mm-hmm.
Okay.
That's what
So,
the B flow is particularly for, is for AI.
yeah, I was kind of surprised when I learned what bfloat actually stands for. It's the brain float, named by Google. That one threw me for a loop. Yeah. Okay. So you mention in the description of the project that it's header only as a feature. And some people today consider header only to be an anti-feature. So I'm just kind of curious if you are, interested in speaking to that at all.
Yeah, I think when developing libraries for people to use, header only is a huge feature. I mean, the standard template library is so popular because it's header only. If it's this massive library, and yet you only have to build the parts of it you use. And so the whole idea of C++ is you're only paying for what you use.
Okay.
So by having it header only now, I don't have the additional binary space of what I've had to build in a library. And I only actually have to build those templates that I'm using. So often I find for low level stuff, you end up with faster build times and less binary by just making them header only. And then once you go to the larger project, then you start making CPP units in order to concentrate where your expensive build times are.
Okay. Well, and a moment ago, you mentioned the Boost ODE library, and I'm curious if you want to, how does Ascent compare to that? Is ODE? I'm just sitting here assuming that the Boost ODE library is also header only because Boost is basically header only. I know for people watch this later, that's an exaggeration, but there's a lot of header only code in Boost.
Right. Yeah. ODE is entirely header only because there's a lot of template code.
So performance-wise, feature-wise, how would you compare them for people who are familiar with the Boost one?
So the Boost one provides some more like implicit solvers versus Ascent is particularly just focused on explicit solvers. And so it has some other features in there that Ascent doesn't have. However, just for explicit solvers, Ascent tends to be faster due to vectorization or automatic vectorization for like standard library types.
Okay.
You can with ODE use custom types, and there are ways to get it to vectorize, but it's not as easy. Okay. And it also requires additional copies if you try to use it for modular simulations. So that's getting low level stuff, but it ends up being significantly more expensive in certain use cases.
Okay. So, I mean, Ascent isn't the reason that you originally contacted me and I asked you to come on for this interview, but just, what state is it at? Is it currently like actively supported, like people should go and check this out kind of project?
It's continuing to be used and supported. Like it's not getting a lot of focus right now because what it is, it works. But I do have long-term goals to make a version 2 of it that will be significantly better as well. But just don't have a timeline for that.
Well, and since it is header only, and I'm just curious, like, were you able to make any portion of this constexpr, or would that be like plausibly on the roadmap for your Ascent 2?
So that's on the roadmap. Yeah.
Okay. I'm curious though. There's so many limitations today for CMath because basically, if you want to do anything interesting with CMath at constexpr time, you have to wait for C++ 26. Mm-hmm. None of the trigonometric functions got in until C++ 26. How much of the standard library, cosine, trigonometric functions do you rely on for something like this?
So there's a variety of answers here. So I have compile time versions of like trigonometric functions that I use.
Okay.
If it can be calculated at compile time.
Okay.
For runtime stuff, I do use the standard library a lot because there actually tend to be very fast implementations.
Right.
And we've even tested using like the fast flags on compilers, and we tend to only get like 5% performance. And you can you don't always know what you're sacrificing there in terms of accuracy.
Yeah, I've heard that described as, if you don't care that you get the right answer, basically.
Right. So we care we get the right answer, so that 5% difference is not worth it.
Okay.
So we just use the standard library like cosines and stuff. However, like when you're writing actual physics code and trying to make it really fast, a lot of time you try to avoid trigonometric functions as much as possible. And so you can do that a lot of times with just things like linear algebra. If you take a dot product, it's equal to the cosine of the angle. Right. So I can just use the cosine of the angle and not actually ever have to do a cosine. Sometimes that's true. And a lot of times you build your algorithms in that way.
Okay. I've spent enough time playing with a 3D graphics engine lately to realize that I have forgotten almost everything that I learned from my linear algebra class in university. So, yeah. Okay, though, you said that you have compile time versions of the trigonometric functions that you use in the cases where you determine that these are things that can be computed at compile time. Mm-hmm. That's the kind of thing that when I bring this up, I hear people say, well, that's ridiculous. Why would you ever need a compile time cosine or whatever? So you've got to tell me more about how and where you use these compile time trigonometric functions. If we can say that word one more time in this interview.
Nice. Yeah. So hopefully I'll be, my company just gave me permission to release a new FFT library, open source. So still working on that some, but it's actually, it has to calculate tons of trigonometric functions at compile time, because it's particularly for solving fixed sized FFTs. So if you know the size of your FFT at compile time, then you can, I don't know if you know anything about FFTW.
FFTW?
Yeah.
No, you're mostly going to lose me with FFTs in the first place. So you're definitely going to have to,
so probably it's the most well-known FFT library. However, it has to do planning during runtime in order to figure out how to efficiently solve the thing.
I see. I can already guess where you're going with this.
Yeah, when you can switch to do things like compile time, well, now you don't have to do a runtime plan. You can do a compile time plan. On top of that, we can do so much with compile time C++ that we can build, they're called butterflies. But that's how you break up your operations in FFTs. You can build these more efficiently. And so we can actually and for certain fixed size FFTs, we can run like 80% faster than FFTW, which is ridiculous because it's extremely well optimized.
Right.
But it's because we can do all these compile time optimizations and inline everything.
Right. That reminds me of Hannah's compile time regular expression. Like if you know the thing at compile time, then how much work can you set up so that you don't have to do it at runtime?
Yeah. And these like 60, 80% we're seeing, that's not even including the planning time. Like that's totally thrown out. This is just actual computation.
Oh. So simply having done the plan at compile time.
Yeah. And then
gives you that much
in. A lot of times when it ends up happening, we found is you can build large tables and then you can reference those tables to calculate your butterflies and stuff. Mm-hmm. But if instead of reading from large tables, you actually calculate the constants in line where the operations happen, then as you're fetching into your cache, your code you're actually running, you're not fetching as much data. And therefore it can then do these larger operations much more efficiently without having to pull and fetch lots of data into the cache.
I want to make sure I understood that correctly. So simply moving more stuff to compile time means that your code is going to be more cache friendly.
Yeah, well, because what we're doing is instead of just calculating a table and reading from that large, massive table, we're calculating the constants and embedding them right where the operation takes place.
Right. Okay. Yeah. So you're relying on the compiler to do an extra level of constant folding for you at compile time. Yeah. Okay. That falls exactly in line with the kind of things that I've seen improvements with constexpr type code. Cool.
Yeah.
I take it it's safe to assume that your FFT library then is also header only.
Yeah.
If it's all templates in constexpr, we don't really have a choice at the moment.
So FFTW is still great if you need something to be configured at runtime.
Right.
I'm not trying to replace that. But if you know you're specifically like, I'm solving this size FFT, then you can gain performance.
So if you don't know the size at compile time, does your library still work? Or you just say, just use FFTW for that?
I would say use FFTW. I mean, you could pre-build various potential lengths, right?
Right.
But if you have no idea, then use FFTW.
So
you said a lot of applications know what they're taking, the window size that they're using. And they might even have like 8 window sizes, and you could compile those 8 sizes.
Okay. Yeah, I can see that. Even though I've never done work with FFTs, I can see that. You said your company is going to let you open source this soon?
Yeah, it should be soon.
Can you give us a preview of like where people should look for it? Is it going to be at on which GitHub?
So I don't know yet, but I'll post a link to it on my Stephen Berry GitHub page.
Okay.
Because even like Ascent, was through my previous company actually, but I still have a link for it there. So.
Right. Yeah, I have to respect you only have 4 pinned projects on your GitHub page, so you have room to add a couple. I recently realized I'm actively working on 16 different projects, so I don't have the luxury of that at the moment. Do you want to give a shout out to your company at all for being so willing to do this, or is that inappropriate?
No, I can give them a shout out. So yeah, I'm working for Matrix Research.
Okay.
They're a small business. Yeah.
All right. So anything else you want to add about Ascent before we move on to Glaze?
I would just say one comment. So in talking about Glaze as well, which is this kind of transition, is in Glaze, we realized that initially we had designed it so we used pointers to store the data that we would then read and write from.
Okay.
And then we realized that, okay, we don't know pointers at compile time. But what we do know at compile time are member variable pointers.
Okay.
Because they're just offsets.
Right.
And so in terms of Ascent, what we want to do in the future is change registering, because what you can do is you can register like, here's my variable, and then here it's just a derivative. Instead of registering that at runtime for the addresses, we can instead say, okay, here's my member variable pointer for the value in its derivative. And now I can do actually all kinds of compile time setup and optimizations for the ODEs.
So because the compiler is going to know the offset into every struct that it wants to actually access.
Right.
Yeah. Okay. I can definitely see that. That makes sense.
So that's something we want to bring to Ascent, but it's a huge part of Glaze.
Okay. All right. So then tell us about Glaze. What is Glaze?
Yeah. So Glaze is most well known for being a JSON library. And that's its primary function. It's a really high performing JSON library, but it's really written to be an interface library, which is why doesn't have JSON in the name.
Okay.
And it also supports reading and writing CSV files, and there's a binary format that we've been working on that it supports as well. And these are all supported through the same API. So you just register your classes or just use the standard library, and then you can read and write to all these different formats.
Is that like a CBOR or whatever for the binary format, or is it something different?
No, we looked at implementing message pack and CBOR and realized they weren't high performance enough from the binary side that we wanted. Okay. So we wrote our own.
Okay. Hey, why use an existing standard when you can make one of your own?
Right. It's always really sad to make a new standard, but the whole point of the binary was to have really high performance.
Okay.
And one really important thing in the binary is like we wanted to be able to just mem copy things like standard vector. Say if it's standard vector of doubles, I want in the spec to be able to just mem copy a thing. But so the binary spec actually maps one-to-one with JSON. It still keeps track of like, is this an array or an object? But it also keeps track of like, okay, the vector has this element size, like it's using a 64-bit value here, and it's a number. So you can actually save the binary out in file, and someone could read it 10 years later and figure out what everything was.
I have to rewind just a moment here, though. When you said mem copy a vector, I want to clarify if you mean mem copy the data that a vector points to?
The data, yes.
Okay. Just making sure.
Yeah, yeah. No, you wouldn't want a mem copy of the pointer and size of thing.
Yeah, just okay. Whew, all right.
Yeah, so when I say mem copy like a SID vector, I'm meaning mem copy the contents.
Sure. Okay,
so
good.
The problem with a lot of these binary specifications is that they come from the age of when we didn't know whether we liked big or little endian, and networking was all big endian. And now everyone's decided for processors we're little endian,
Right?
pretty much across the board. But it means that all these specs require you to swap endianness.
Right, because they all expect to do things in network byte order.
Right, which is a ridiculous performance overhead, because a mem copy gets essentially vectorized. Like I can do, like I can normally do like 8 or 16 at a time. So I'm talking a performance hit of maybe 16x plus the cost of the swaps. So you're like 20 times slower just because you need to swap into big endian.
Interesting. So it's been long enough since I've done network programming. Oh, goodness. It's been a long time now. 15 years. No, anyhow, 13 years. That I just hadn't even crossed my mind that could be a significant performance bottleneck. So you just say, forget network byte order. We're little endian. Everything's little endian. Okay. So everything little endian right now. ARMs are still technically switchable, right?
Power PCs, I think, are switchable.
Okay.
I think some ARM chips are, but most ARMs are. Even Power PCs are not default little endian.
They just all boot to little endian.
Yeah.
Huh.
Which I heard, I don't know. So what I heard is that the reason why is because when you cast a 64-bit int into the 32-bit int, it's cheaper on little endian. You can just chop off.
That sounds believable, but those decisions were made. I mean, Intel standardized on little endian long before they cared about 64-bit integers, right?
But I think it helps you go from a 32-bit system to a 64-bit system.
Maybe.
And make them compatible. Right. I'm not exactly sure why everything is moved that direction, but I'm glad it's all standardizing.
So let's make sure that we're all on the same page here, and for the sake of our viewers/listeners, since this could be done either way. Little endian is where in memory, the first byte is the lowest order byte. Is that correct?
Boy, I don't know the terminology even.
Okay.
This sounds right.
I'm pretty sure that's right. Okay, so you kept saying that Glaze is like way faster. How much faster than your competitors? So
in terms of, there's like some performance benchmarks on the site. There's a library called SimDJSON that's in C++.
Yes. That's the fastest one.
If you're just going to be if you're searching, say you have a massive file and you're just searching for one element in the file, that is your fastest library to do that. And you should use that. However, if you're reading in a file, like I just want the entire thing populated in C++,
right?
Then Glaze is pretty much the same speed. And it's faster if data is not in your expected sequence. So what that means, JSON is an unordered map structure, right? So the keys, when you read in via SimDJSON, it has to, if it expects it, if they're all in sequence, it can just read one, read the next, read the next. If any one of those is out of sequence, it has to jump back to the beginning and reparse the whole thing.
Oh, okay.
So the moment something's out of sequence, SimDJSON's performance just tanks.
Okay.
So for large files, like we could make a test that shows Glaze 1,000 times faster. It could be arbitrarily faster because
you could make the data as poorly ordered as possible.
And the whole reason is because Glaze is using hashing to find locations, whereas SimDJSON has to scan.
Okay.
But SimDJSON does a bunch of like low-level SSE intrinsics in order to scan very, very fast. And we do, like I said, that like 8 bytes at a time scanning. But if you have really wide registers like AVX 512, then SimDJSON is going to be the best way to go.
Okay.
Just for scanning.
Now, you said, you kind of at least implied that Glaze is not really meant to be a general purpose JSON library, which is why you didn't put that in the name. But I mean, can I use it as one? Can I just load up a JSON file and have an object model and pretend like I'm using nlomon JSON, which literally everyone watching this has probably used at some point?
Right. So we have a structure called JSON_T, which basically does the same thing that nlomon or whatever is. But the thing is, the moment you go to that context, you have massive performance hits because you have to start heap allocating things.
Okay.
So the idea of Glaze is that we have the memory in C++ that we already want to work with. Like even in nlomon, I would say like .as and convert the thing to whatever I wanted, right?
Right.
So the idea is let's get rid of all those cast conversions. We don't need those because we already know that here's the structure I want. So we just read directly into the memory of the structure.
Okay.
So I will note too, like SMT-JSON doesn't have writing. So if you want just a fully featured read-write, then Glaze is great because you can do both.
Okay.
And it's also it's currently the fastest writer in the world.
Okay. But so if you know what your structure is now, forgive me if you already explained this, but you can, it sounds like, give a C++ class and say, map this onto this JSON file.
Right.
Okay. And
so it also works with all the standard library containers as well.
Okay.
So maps and sets and decks and vectors. So you can just read and write directly into those things. So if I have like a JSON array and I want to read it in, it can just read it directly into a std vector.
All right. So we already had the like reinterpret cast conversation. How do you make this magic happen?
So it uses a lot of concepts.
Okay.
And it's just basically going to say, okay, if I already have memory for this vector written, so say I've read in once, then it will just overwrite the values that already exist, so I don't have to do any new allocations. Obviously, if it's the first time I'm reading it in, it's going to have to emplace back those values and have a heap cost if I'm reading a selected vector.
Okay. So you just overwrite like in a mem sharing almost.
But oftentimes in JSON context, you're reading and writing the same kind of messages again and again. Right. So it makes sense just to reuse the memory.
Right.
And so if my map or my vector is that I'm constantly reading into, if I don't have to reallocate that thing and I can just overwrite the value and just literally parse into that value is what we're doing.
Okay. And so now I have to ask also, what's the like constexpr story here?
Yeah, so a big part of it is we want to be able to make interfaces and be able to serialize structures without actually having to touch any of that code. Because I want somebody to build an API to their code base or serialize something without ever having to change any of their own code.
Okay.
So what you can do is you can say, okay, I have some class that I want to serialize. And then you template specialize a Glaze structure called meta with your. So that means your template specialization can live wherever. Like it could live in some other header, right? And doesn't have to touch the original code base. And then what you do is you just register the kind of structure. You do a static constexpr value, and you assign that thing whether you want it to be a JSON array or an object. And what it is it's just basically a tuple of like strings and member function or member variable pointers.
Okay.
So we can't do pointers, obviously, because they're not compile time known. So this is where member variable pointers come in. Right. And so you just say, okay, here's all my member variable pointers for my class. I can now make that compile time tuple where I know all the names associated with those things.
Okay.
So that's basically building the reflection part of this. Right. So part of the architecture too is so C++ is moving towards getting reflection, hopefully sooner than later.
Certainly by C++ 29, I'm sure of it.
Hopefully. But the idea is that all those meta classes that we have to write right now, you'll be able to just delete them. And once we have reflection, and the library will still just work.
Okay. So right now, you, the user, has to define the reflection interface, yes, which, to sum up, as my understanding, was a compile time map of names to member function pointers.
Yeah.
That sounds like a really clean way to do that, actually.
So what happens underneath is, so basically it starts off as a tuple of these names and member variable, or you can also do member function pointers.
Right.
because you can invoke things in the library as well. But that then gets translated into these compile time maps, which then store a variant of all the member function pointer types. So not a variant. So because each member function pointer has a specific type, right? Whether it's associated with a double or a vector, or so we make a compile time variant of all those types.
Yeah, but you can have multiple member function pointers that are effectively the exact same type, right?
Correct. So your variant. So if you had just a bunch of doubles in your class, you'd only have one type in your variant.
Okay.
But in like JSON objects, you have all kinds of things you're combining. Like in your struct may have all kinds of types in it. So this way you can register all your different types, but it makes a variant of those things that then when the map lookups, it gives you a variant that you then call the library underneath calls a visit on.
Okay.
So that's how you get the runtime behavior of the access.
Okay.
To the type.
All right. So there's a feature that you mentioned. It was the whole reason I asked you if you wanted to do an interview. My first interview in a couple of years now, it feels like. Actually, something like that. And you said that like there's a way with like mem sharing for different processes to be operating on the same JSON structure at the same time. Did I understand that correctly?
I think you were referring to the shared library.
Okay.
Interface.
Shared library.
Which is not sharing it's not like parallel thread sharing. It's shared library interface building. So what this means is, so we can have shared libraries on like any of our systems, right? So there's code to build the proper DLL on a Windows or shared library on Mac or Linux, right?
Right.
And what happens is, what we were finding is we were building specific APIs for our shared libraries for each of our projects.
Okay.
And what we wanted to do is just have one single interface for every single DLL we ever make.
Okay.
So, but we need performance. So we need to have direct memory access across the DLL boundary. Okay. Because what we'll do is we'll just read a bunch of pointers, set up our interface, and then just run. Because we don't want any costs of like lookups and access. So we do our access at initialization. And so that's where there can be some overhead. But then I just want the pointer to read and write from. And that's memory inside the DLL. So what Glaze gives you, it gives you an API that you can use cross-platform for all these different kinds of shared libraries. But the API lets you access a direct memory pointer based on JSON pointer syntax, which is a specification that says I can write. So say I have some object that has like a class called animal, and then inside that is like age. I can do like /animal/age in string. I give that to the DLL. It gives me back a void pointer. This is underneath what it does. Okay. However, like what we're trying to do is we want to make this thing type safe. And when you work across DLL boundaries, that can be tricky.
Right.
Like standard any only works in its own compile time context. You can't pass it across a DLL boundary. Okay. Because it's basic like its type info pointer, the way it does its hashing, is only valid in that compile time context.
Okay.
So what we do is we have a hashing algorithm that looks at a ton of parameters on your class or type, and also a name. So everything that gets named, if you don't have a name, it's just like unknown, and then you can give it a name, and it'll just hash on the other qualities. But double, like the double value in C++ just has the name double, and that gets hashed into a 128-bit hash. Okay. That hash happens on both sides. So on the DLL side, and then on the user side, whoever's using the DLL, and then that hash is compared every time you access something. Okay. So getting that pointer originally has some overhead, because now these are all compile time hashes, but you have to compare two 64-bit integers to make sure that this thing is valid.
So how do you or do you attempt to then mitigate against other possible ABI issues by saying, oh, I don't know, the layout of some struct is different from the DLL point of view versus my point of view or whatever?
Right. So part of that hash that goes into like objects is like obviously the size of the object. We can even check the compiler that we're building with. We can check, is it trivially copyable? We check, we have tons of type traits in C++. We just check them all. So if you change something like to just changes behavior or size, then it'll automatically catch that.
Okay.
There's also a version tag that the user can change and say they can bump the version tag and then your hash will be different.
You said you can execute functions in your proxy definition as well, right?
Right. So as part of this, we want functions to go across the API as well. So the API allows you to actually pull a standard function across the DLL boundary and then invoke it on the other side.
Okay.
So you can also pass parameters and call like member functions on classes. Just by you pass in a bunch of values and those get converted to void pointers with hashes and they get checked on the other side that they're the valid types.
Wow.
And then it calls the function.
So what you said at the front that you prefer to write everything in a kind of cross-platform safe way. What platforms do you currently support for Glaze?
So we build with GCC, Apple Clang, and MSVC.
Okay.
And so those get tested just automatically on GitHub Actions.
Right, sure.
And so, we support basically anything that supports those compilers.
Nice.
So we're building, currently using it on, like I'm using an ARM, tiny ARM chip on FPGA board. And then we're also using it on a massive server. So yeah, it has to be used like everywhere. And part of this also brings up then, so Glaze is written so it doesn't throw exceptions, so that it can be used in really tight embedded environments.
Right. Okay.
And you can use it without requiring heap allocations.
Nice. Have you, are you able to, or have you run it through all the various sanitizers on these platforms as you're testing these things?
We've used Clang Sanitizer, and we actually do have a sanitizing test.
Okay.
The funny thing is, like, for that one undefined behavior thing, we have to turn off the sanitizer for that little piece of code.
That one little piece of code where you're talking about reading past the end of an array.
Yeah.
Yeah.
Yeah, where we're reading. Yeah.
That was the thing that that made me wonder about that. Yeah.
Yeah. So yeah, it actually uses a sanitizer every time when we do our actions as well.
I'm kind of mentally coming back to this ability to do like remote procedure call kinds of things across DLLs. And it's just making me think of the old school DLL interface that Windows used for Visual Basic and all that stuff. Do you know what I'm talking about?
I'm not sure.
I'm going to attempt to do a quick search. I cannot remember what it is called, but man, and I used it for so much of my career. The idea was, you could just have a Visual Basic DLL imported into a Visual Basic project, and you would be able to discover the functions, the classes, all of the things that were available in there because they were all kind of exported in this generic way. And lots of DLL communications on Windows back in the day used that capability.
Yeah, so that's where we're using JSON as like, here's how we specify our API.
Right.
And so then you can dump out JSON schemas, which then can also be loaded into like Visual Studio Code, and it will it'll autocomplete for you, and it'll tell you that, okay, this wasn't a valid type that you tried to put in here.
Wow.
So it gives the user like immediate feedback. But also, you can then just hand someone a DLL, have a function that just dumps that thing out and says, oh, here's my API to the DLL.
Right.
And it's the same DLL regardless of what class. So basically, you can just make whatever class you want in C++, make a meta for it, and then you can just have a DLL interface and don't ever have to worry about building DLLs again.
So you said like the first time I want to do like one of these remote DLL function calls, it can be kind of expensive because it has to compare all the hashes and give me back a pointer to the thing. Got that right? Okay.
Yeah.
And then after that, have you measured like what this performance overhead looks like?
So there's basically no performance overhead because you're just directly addressing the memory.
Right. So you just take that pointer, cast it to a function pointer or whatever, and move on with your life or whatever.
Yeah. So they're like get functions, and you just say the type that you want to get. So it just looks like a normal, like you'd be static hash to this. You just say get this type, and that automatically does the hash checking underneath. And then it'll give you the pointer of the type back. Okay. So now you just deal with it like you would normally a pointer in C++.
So is there any capability then, like going back to my original misconception, is there any capability for cross-process interaction using this tool?
So that really would have to be like a higher level.
Sure.
Because this is all, so you're not building like standard unordered map, right, is not thread safe.
Right.
So you could have your own thread safe library that you then use with the library.
Okay. I see.
So,
yeah. So it'd be too risky. You're not going to share these data structures across processes because you don't know what they're going to do.
Well, the thing is, again, this is an API to your data structures or the standard library data structures.
Right.
It doesn't create, like the JSON_T is like the only data structure we create, and typically you shouldn't be using it. So for most part, the library isn't making data structures. It's just interfacing with data structures.
Okay, cool. Well, that all sounds very interesting. And so this is production code currently being used as well?
Mm-hmm.
Okay.
Yeah. It gets used all the time now.
I just realized that's interesting. GitHub doesn't detect which license you have, even though you have a license file in here.
Yeah, so I had to figure out how to do that because we added a note for like embedded situations of not needing to include the license. Which I think Boost does the same thing.
Okay, yeah, that sounds about right. That the Boost library does something like that, yeah.
But then it makes it so it doesn't pop up as MIT, but as MIT.
So it's MIT with an extra exemption that it's even freer if you're in an embedded scenario.
Correct.
Pretty cool. Was that true as well for your other libraries?
It's actually Apache, but it's also a pretty liberal license.
Okay. Now, I am kind of curious, like, what was your original genesis for this project? Why did you decide I need to make a super fast in-memory JSON thing?
So I wanted the same API to go across DLL boundaries and be able to read in configuration files.
Okay.
And so part of that was just going, okay, I need to read and write from the direct memory because I need direct memory access for my interfaces. And I wanted to interface through like JSON pointer syntax.
Okay.
So that was a motivation. Motivation for like the JSON library was we realized like we had been doing things in a scripting context. We had used KaiScript and then realized there was a lot of overhead there.
There is some overhead there, in fact, yeah.
And so by going to a JSON library, we could push our performance. And also we had then had to write our own so we could still build logic. We needed some sort of like event structures and stuff to be put into our input files.
Okay.
And so the library Glaze also allows you to register your reading and writing handling for any custom types. So you can configure it however you want.
All right. Let's see. Is there anything else that you'd like to talk about before we wrap this up?
I thought it'd be interesting to bring up exceptions and error handling in C++. Because I learned a lot about this through Glaze.
Okay.
At first I was thinking like, okay, like maybe people say like they don't use exceptions because there could be performance overheads, which is true in the exception case.
Right.
But what we found is that we're using standard expected, which is C++ 23 thing. We have our own implementation, which is just the same as the standard for C++ 20 right now. But when we moved over to it, we found we lost performance over exceptions.
I believe you, but let's go ahead and let you explain why.
Yeah. So So one of the things is you constantly have to be checking for if you're in error state and then returning.
Right.
And so just those Boolean checks and the branching that you're creating makes it more expensive. Whereas the exception can just propagate all the way out to wherever your try catch block is.
Right.
So what we did find is that if we inline all our pretty much the Glaze code, because it's all compile time, a lot of it gets all just inlined with each other. And if after every single function call we check if there's an error, compilers like GCC and Clang, MSVC can do a bad job of this, but GCC and Clang will actually eliminate most of those checks because it can short circuit it.
Okay,
However,
that's actually very interesting.
It's really interesting. However, it needs to be after every single possible error. So every single function we call that could produce an error, we then check if there's an error. So there are two ways to build this standard expected handling. Is you could just return a standard expected from your function, right?
Yeah, that's the
check,
method that everyone talks about.
That's typically what everyone does. It's annoying for syntax because you have to say if this thing, right? And you have an if block on the check and you return. So what we typically do is we have like a context that we pass around and then we assign into an expected. But either way, you have to have an if check and then return to short circuit it. You could in all your functions at the very top say if there's an error, just return so it don't invoke me basically.
Yes.
But the problem is that, and that's so much cleaner to write because now I can just write a bunch of functions and it will just skip all of them.
Yeah.
But the thing is, it's still going to hit all of them. So I still incur the overhead of the function call. And the compilers we found can't as well just eliminate all those checks. So it ended up being that the fastest way to do it was to always check the expected and return if error on every single function call. So we might have like 30 function calls inside a function call and we have 30 checks.
That makes me sad.
It's very sad.
So to match exceptions performance with expected, you had to vastly uglify your code.
Yes. So this is where, for like most developers, I would say don't go away from exceptions. Use exceptions in C++.
Right.
Unless you actually expect to hit an error case.
Just for the record, that's why ChaiScript is slow in some places, because we abused exceptions.
Right.
It's a lesson learned.
In JSON, yeah, you use it for like the function deduction, which function to call.
Oh, well, a lot of that's actually had been eliminated.
Okay.
A while ago. What we did was we tried to call every single function overload. If it couldn't call it, an exception was thrown. I moved on to the next overload. Then I moved to various levels of filtering and like looping instead of just, waiting for an exception to be called. But it's still expensive because, the combination of function overloads with implicit conversions allowed is just very complicated to sort out at runtime. But the real problem is return statements, break statements, and next statements are all exceptions because it's the cleanest way to actually get back to the previous control flow and continue again. Yeah. Anyhow.
Gotcha. So exceptions are still the cleanest way to do in C++ if you want performance.
Now I want to know, when you were done doing this check after every single function call, did you end up with code that performed the same as exceptions, worse than, better than? Like, where did it fall out?
It is still slightly slower than exceptions.
You really need to present this at a conference, just so you know.
Yeah, Herb Sutter has a paper that solves this and discusses, what's it called? It's called Zero Overhead Deterministic Exceptions.
Yes, but does it actually fix it? Because his still require an implicit check written by the compiler for every one of those function calls. Ooh, but you're saying if the implicit check was written by the compiler, then it might be able to optimize it out.
So I think his paper is probably, I need to read it in more detail and then get a more full view of this. But the reality is, like, for C++, if we want to be able to write the fastest code possible and write somewhat clean code, we need a new error handling approach.
Okay.
Well, I think I should let you go here. Thank you very much for being my first ever interview on C++ Weekly. And is there anything else that you want to leave our listeners, viewers with before I let you go?
Well, I just want to credit my coworker, Michael Walcott, for a lot of the Glaze development and a lot of so many good discussions on like how to design the thing. So a lot of these things are not just my own discoveries, but yeah, peer programming with someone.
Well, very good. And I'll make sure that there's links to your projects and anything else that you want to send me in the video description.
Sweet.
Thank you.
Thank you for your time.